Thank you, Camille, and thank you everyone for being here. I'm really excited today to talk to you about the question of whether these rogue worlds we've been talking about might have small orbiting companions of their own. So I'd like to start with this graphic here, which shows the different types of objects that we might think about having orbiting companions. So in our own solar system, we have giant planets, we have low mass stars throughout the galaxy, and then we have the rogue worlds, which can be a mixture of the giant planets and the brown dwarf mass objects. Then we know that in our own solar system, the giant planets have many moons. The moons outnumber the giant planets in our solar system, something like 20 to 1, especially the more massive ones, where Saturn has over 100 moons. And likewise, low mass stars we know have many orbiting companions of their own, at least one per star on close-in orbits based on surveys such as Kepler and TESS. So what about these objects in the middle, the rogue worlds, the planetary mass objects, and the brown dwarfs that we've been searching and discovering with direct imaging and with microlensing surveys? These objects present us a really great opportunity to study the populations of companions to these objects in general. So a brief note here on semantics. I'm going to call the companions to rogue worlds satellites. This is because I don't know what else to call them. They're probably not planets if they're orbiting planets themselves. And I'm not sure that you can have a moon if you're not a planet orbiting a star. So let's just call them satellites and we'll discover them and then someday we'll figure out what to call them later. Okay. So the method that I want to talk about today is the transit method. We haven't heard much about that yet in this conference, so I'll put up this little animation. Basically, the idea is we're hoping to find companions that are very precisely aligned between the object they're orbiting and our line of sight in our telescope. And we're looking for small dimming in the brightness of this object as the companion moves in front of the star, or in this case, the rogue world, and blocks part of its light. If we see this happening over and over, we can infer the presence of an orbiting companion. But instead of what we normally do, which is we look for a planet transiting in front of a star and blocking the light of its star, in this case, we're observing these free-floating planets, these free-floating rogue worlds, and we're looking for cases where an orbiting satellite or a moon-like object or a planet analog transits in front of the rogue world itself, like that. I have about a 1 second delay between my screen and that screen up there. So the idea of looking for companions in this way comes from Marianne Limbach. At the time, she was a Texas A&M graduate student. Now she's a research scientist at the University of Michigan. But I want to make sure I give credit to her for this idea, which has kind of launched us down this pathway of trying to make these measurements. So let's imagine what we would want to do if we wanted to design a survey to find the satellites orbiting rogue worlds. So one design configuration that we want to do is what wavelengths do we look at? Rogue worlds themselves do not fuse hydrogen. They're substellar objects, and they're faint and therefore cool. So how can we get enough transit signal to observe these transits? And the answer is that we want to look in the infrared. And in particular, we want to go to long thermal wavelengths. So the first searches that have been done have been using observations from telescopes like Spitzer. I also want to mention the PINES survey by Pat Tamburo and Phil Muirhead et al., which used an infrared detector on the ground. But the most sensitive ones have been done with Spitzer in the mid-infrared or the near-infrared bands, the 4 to 5 micron bands. This is work that was led by Marianne as well. And basically what Marianne did was she took observations of these objects that had been made to study the variability of these rogue worlds to look for changes in their brightness due to spots or other storms or activity happening on them. And she looked for little dips in the brightness. And she found one candidate. This is a relatively low signal to noise detection here, but this dimming event could be the indication that there's about a 1.7 Earth radius satellite orbiting this object. This is relatively low signal to noise, and with only a single transit, we can't confirm that it's real, but it's a good motivation to continue. So if you were to take all of the observations, all of the different stars or rogue worlds that Spitzer had observed, which was about 44 at the end of its mission, Marianne did an injection recovery test where she calculated that if there were many of these objects, many super Earth-sized satellites orbiting these rogue worlds, we probably should have seen something compelling. And because we didn't, we can put upper limits on the occurrence rate. So we can actually already place limits on the presence of companions orbiting around these objects, even though it's perhaps not super surprising that we don't see anything this massive around such low mass objects. So this brings us to another challenge. we look at the Spitzer data and we see that the signals that we're looking for are small and the data are noisy because these rogue worlds are so faint. So how can we get enough signal? How can we increase, even after we go to the infrared, our signal to noise so that we can detect smaller and smaller satellites? And there's one relatively simple solution, which is let's just use a bigger telescope. So let's take Spitzer, which had a relatively small angular or telescope diameter of about 88 centimeters, and let's replace it with a 6.5 meter telescope like James Webb. And it turns out that this really helps quite a bit, as you might imagine. So we get very good sensitivity to much smaller objects with JWST and observations of these rogue worlds. I'm not going to go too much into this because Michaela is going to tell us about this in about 3 talks. But you can actually detect solar system-like moons around these objects if they were there in the handful of cases where we've looked. Okay, but there's also another way that we can improve our signal to noise, and that's by observing the relatively easiest to observe rogue worlds to search for these objects. And in particular, what we want to do is we want to look at young ones, the ones that are still warm from the recent formation and have not yet cooled off and grown fainter so that it's harder and harder to get enough photons to make these measurements. So let's go look at the newly formed rogue worlds. As we've seen before, this is how objects like planets and brown dwarfs cool off over time. And you get this very constant power law cooling for these objects. So the younger and younger you can push, the brighter and brighter these objects can be, and the easier it is for us to potentially detect companions orbiting them. Okay, so the third challenge is that when we use the transit method, we have to rely upon the very precise alignment between the object that is going to be orbited, in this case, the rogue world, the thing that is transiting, in this case, the satellite, and our telescopes. And in most cases, this is not going to be this is not actually going to happen. We're not going to have this alignment. Most objects that are going to be orbiting in the population of these rogue worlds are not going to be aligned with our line of sight. So in order to detect things using this method, we need to observe many of them. We need to look at many, many different objects so that occasionally statistics will tell us that we should get some fraction of them that happen to be in our line of sight. So this pushes us towards a survey that might observe many of these, perhaps even hundreds or thousands. And that way we would build up the statistics high enough to be able to detect these. So one thing that we can do is we can look at star-forming regions where there's many different objects that we can look at in the same relatively small field of view. So consider here the Orion Nebula Cluster. This is about a 3 million year old star-forming region. It has many, many free-floating planet mass objects. And it's relatively nearby compared to other star-forming regions, so we can get lots of flux from these objects. But even this object, even this star-forming region is pretty far away compared to the objects that we were looking at with Spitzer. The object that Michaela is going to tell you about in a couple of talks is only 2 parsecs away from us. Orion is 400 parsecs away. So we're still really pushing up against our limitations in terms of how many photons we need to make these discoveries. So the answer to this problem is we need a relatively large telescope with good sensitivity in the infrared to do this. And we also need a big field of view. We need to be able to cover this entire region of space in order to see all of the different free-floating objects and rogue worlds that we can monitor. And all of this is pointing us towards what if we took the Roman Space Telescope and did a survey like this? Roman is going to launch next year. We're still on time, Scott, I assume. Yeah, I get thumbs up. So we're launching next October. It's going to have a 2.5 meter diameter, a 0.3 square degree field of view, and it's optimized for infrared observation. So this kind of checks all of the different boxes I'm talking about. We get lots of photons, we get big field of view, and we watch in the infrared where these rogue worlds are going to be brightest. And as a result, we've been thinking about and trying to build support in the community for this TEMPO survey. TEMPO stands for Transiting Exosatellites, Moons, and Planets in Orion. This is a joint venture between myself, Marianne Limbach, and Melinda Soares-Furtado. So here's the basic idea. We take our Roman field of view and we plop it down on Orion and we just stick it there. We don't try to slew, we just leave it there as solidly as possible. And we observe for something like 15 to 30 days. And we just take measurement of brightness over and over and over every 18 seconds. The filters that we have at our disposal are very well matched to the brightness, to the spectra of 3 million year old planets like we'll see in Orion. This is a model of a 3 million-year-old 10 Jupiter mass object in blue here. And these are the two filters that we are considering using. So we have this wideband filter here, which maximizes the number of photons. And then we have effectively a K-band filter here, which is better for the coolest objects and prevents saturation on some of the brighter objects, but overall is a little bit less efficient because you're throwing away more light. So we have different options in terms of ways that we can carry out the survey with Roman. So this is just a sketch of what a notional tempo design might look like. We're imagining something on the order of 30 days of observations. That's something we may change based on the realities proposals, but it seems plausible to me that this is something that we could get from attack. We could split this into two segments spread out over a couple of years. That would allow us to make very precise proper motion measurements to verify that anything that we see is in fact associated with Orion. And even if not, we can even measure potentially whether there's a higher velocity dispersion for these objects. If, for example, they were formed by dynamical ejection, like we were talking about in the previous session. We would be able to observe objects less massive than about 0.2 solar masses without saturating, but we may be able to push that higher. So in addition to observations of free-floating planets and brown dwarfs, we could potentially detect planets around young M dwarfs as well. And in total, we would monitor about 2,000 M dwarfs, about 500 to 600 brown dwarfs, and about 400 free-floating planets that are all associated with the cluster, plus many field stars that are not associated with the cluster. This is not part of any of the predefined surveys, so it would need to be proposed through the GEO program. And that's something that we're thinking quite a bit about as the first call for proposals has now been released by Roman. And the really exciting thing to me is that the yields that we expect based on plausible guesstimates of what the fraction of free-floating objects that might have companions is pretty high. So using kind of a standard set of assumptions based on what the occurrence rate is of planets around low-mass M-dwarf stars, what the occurrence rate is of moons around giant planets, both from theory and in our own solar system, we estimate that we might find up to 22 satellites orbiting planetary mass objects, and perhaps even up to 100 objects orbiting brown dwarfs. And since we don't really have any objects in any of these around orbiting any of these types of stars, even a single discovery of this type would be pretty impressive. I'll say there may be cases where we have microlensing observations of brown dwarfs that have orbiting companions. I'm not 100% sure what the status is of all those. So if I said something incorrect there, where I said, perhaps 0 should be 1, then my bad, I'm sorry. And anything that we discover would be in a totally different parameter space, in a different regime than the moons and planets that we have found before. So in all of these plots, I'm plotting the known exoplanets in the black, and I'm plotting tempo discoveries that we expect to make based on these relatively typical assumptions in these orange triangles. And in terms of the mass of the object that we discover and host star mass, on this axis, we see that these pretty significantly stand apart from the known population. Same thing with age and with host mass or satellite mass. And finally, it's separation in mass. So this is definitely probing a different regime of planet/moon/satellite formation than we've ever seen before. So this all sounds cool to me, and I feel excited that we should do it, but is this even feasible? One possibility is that if we look at rogue worlds that are so young, there may be things happening in their light curves that can prevent us from making precise brightness measurements needed for transits. They may be accreting material, they may be occulted by clumps of dust and disk material. So it would be really great if we could observe some young free-floating objects now to make sure that a large Roman investment isn't going to waste. And happily, the JWST TAC agreed, and they were willing to let us take some observations for about 48 hours of some objects in Orion. And we recently got the data. These were taken in October. We've been processing it and developing pipelines to deal with it. And now we have looked at 3 different free-floating objects, and I can very happily show you the light curves that we've discovered. So it's these 3 objects right here. We just chose them at random from the ones that are in our field where we have observations in 2 colors. With JWST, we can use NearCam, which gives us simultaneous observations in 2 different band passes. And but only reach a quarter of the field gets observations in both band passes. So this is from that special subregion. And this is a proposal that was led by Marianne Limbach. So here's our first observation. This is a relatively quiet light curve. The blue points are the blue filter. The red points are the red filter. We split the two visits by about a day and a half. This is to give us time to downlink the data, and also gives us a little bit longer of a baseline for the variability studies that we can do with this. And what we find in this case for this particular object is that we achieve good photometric precision. In fact, in particular, good enough to detect satellites. So there's nothing weird happening in the light curve that would prohibit our ability to make these measurements and to find small things that we're orbiting. So that's good news. Let's look at the next one. So this one, you can start to see some variability. So clearly, this object seems to be a little bit more heterogeneous on its surface. We're not entirely sure what's driving this yet. Could be spots like we see in stars. It could be atmospheric patterns banding like we see on planets in our own solar system. But definitely something is happening. And it seems to be modulated on timescales of a day or so. So this is kind of what we expected. But the surprise was this third light curve here, where we see what looks to me like a flare. Now, I've looked at many light curves of stars, and if this were a star, I would have confidently told you that's definitely a flare, but I actually didn't know that planets could flare. And that was the reaction of everyone I've told about this as well. So if any of you think differently, please let me know. We'd love to hear your thoughts. And the other very strange thing about this is that the flare seems to be higher amplitude in the red than in the blue, which is the opposite of how it works on stars. And I'm really struggling to understand how that could be. I've had a couple of ideas. Marianne's idea was that this is reprocessed light. Maybe it's hitting a dust cloud and the dust is then, getting warmed up and this is getting reprocessed as black body radiation at a cooler temperature. Although I would think that the fact that it has such a sharp beginning would make that hard to believe. My idea was emission lines. Maybe there's really strong emission lines in the redder band that are not in the bluer band, but that doesn't appear to be the case. In fact, it appears to be the opposite. The strongest emission lines are in the bluer band that we're looking at. So we're kind of flummoxed, but I think that this is a really good piece of evidence why we should look at many of these rogue worlds with photometric monitoring. We've looked at 3 of them so far at such a young age, and we've already found something that we can't explain. So if we extend that by a factor of 100 with Roman, it would be really exciting to see what new things we can discover. So with that, I'll put up this summary, which is that transit observations have the potential to reveal the population of satellites orbiting rogue worlds, and it turns out also reveal new insights about their variability. So let's go take a look. Thank you.
You didn't mention the spectral type of those 3 objects. Is there spectra?
They're not in our program. These are objects that I believe were observed in previous Orion observations, so there might be spectra. The masses are something like 8 to 10 Jupiters.
But where does the mass come from? I'm afraid that they're contamination. Like that's what happened with the jumbos.
Right.
So that looks like an M dwarf. That's just an M dwarf flare that's going on, just as a cautionary tale.
Yeah.
These very well, you might be doing a great job of discovering that there's some contamination in the.
That's right. So I believe that these were observed by Hubble previously, and they used the water band filter to rule out background contamination. But I can double check that for sure.
Yeah, and just one follow up on that too, because from the low mass, from the M dwarf side, you said there's 2,000.
Yeah.
You're going to have complex rotators in there.
Yeah.
Brown dwarfs are going to show you weather.
Yeah.
So you're going to have this library of crazy. Just can you comment on how you're going to differentiate all of those?
You mean from transits or just in general?
Yeah, from the transit.
Yeah, well, certainly the variability is challenging for the young stars as well, and we've got a good bit of experience with that. I would typically want to see that it's stable over many, many years potentially. So potentially what you would do is you would find a candidate with this small number of observations here and then follow it up in the future with Hubble or JWST to see that the transit remains coherent while the other activity features, the other complex dust clumps seem to be moving around. We've had good luck doing that with observations of young stars as young as 3 million years. And then, in particular, some of these have very clean looking light curves. So if you did see a sharp transit that looks like it's stable over the small observing baseline that we have, that would be a good indicator of a candidate. If I saw something similar in a much noisier light curve, I would start to feel very nervous. So certainly this would be the very beginning of a long, term campaign to follow them up and confirm them. But I think this is the way to go if we want to do something like this.
Unfortunately, we have to move on. Let's thank Andrew again.